Hello, my name is Gali, and I'm a PhD student at the Technion, Israel. This paper is a joint work with Professor Morris Herlihy from Brown University and my advisor, Professor Erez Petrov. In our work, we present VBR, a new manual reclamation method. VBR maintains lock freedom and bounds the number of retired objects that cannot be reallocated. In this sense, VBR is the strongest among all existing safe memory reclamation algorithms, as it suggests a zero bound on these objects. VBR is highly efficient and does not incur a high overhead when integrated with an existing concurrent implementation. VBR is also applicable to unknown lock-free data structures. Finally, as opposed to existing manual reclamation schemes, VBR is fully optimistic. It allows threads to access reclaimed memory, both for reads and for writes. Manual reclamation methods rely on retire invocations by the program, announcing that a certain object has been unlinked from a data structure. After an object is retired, the task of the memory reclamation mechanism is to decide when it is safe to make its memory space available for reallocation. Previous works defined the set of desirable reclamation properties. Safe reclamation algorithms should be fast and applicable to a wide set of concurrent data structures. In addition, reclamation schemes should be robust. At any given moment, the number of retired objects that cannot be reallocated should be bounded. In particular, a slow executing thread should not prevent the reallocation of an unbounded number of retired objects. Conservative manual reclamation schemes can be roughly classified as either epoch-based, pointer-based, hybrids of these two approaches, or optimistic access. Epoch-based schemes are often fast, but they are not robust. A stalled thread may prevent the reallocation of an unbounded number of retired objects. At a worst-case scenario, these objects will consume too much memory space, resulting in blocking all new allocations and foiling system-wide progress. While pointer-based methods can guarantee robustness, they incur significant time overheads. Using expensive memory synchronization fences for each memory access often results in poor performance. Furthermore, in terms of applicability, pointer-based schemes are not applicable to many concurrent data structures. Hybrids of these two schemes are often performance-oriented. Their robustness and applicability depend on the specific algorithm. Optimistic methods allow threads to access reclaimed memory while taking care to preserve correctness. Optimistic executions guarantee robustness along with high throughput and applicability. However, previous optimistic methods did not go all the way. While reads were executed optimistically, writes were handled with pointer-based approaches, limiting the benefits of the optimistic approach in terms of performance. Our version-based reclamation algorithm, VBR, is the first fully optimistic solution to lock-free memory reclamation. Moving on to VBR, it clearly satisfies all of the desirable properties. First, retired objects can be immediately reallocated, which sets a zero bound on the number of retired objects that cannot be reallocated. This obviously yields robustness. In terms of performance, as we show in the evaluation, VBR outperforms other safe memory reclamation methods. It optimistically allows access to reclaimed objects while avoiding expensive memory fences for pointers protection. Finally, thanks to its small set of assumptions regarding the original implementation, VBR is applicable to all known log-free data structures. Here are some well-known concurrent data structure implementations that can be easily integrated with VBR. In particular, pointer-based reclamation methods are not applicable to the algorithms marked in red. As opposed to most pointer-based methods, VBR is applicable to these algorithms as well. I'm now going to give a brief overview of VBR using a linked list example. For ease of presentation, each list node has a single immutable key field and a single mutable next pointer field. Similarly to many epoch-based reclamation algorithms, VBR maintained a global epoch counter. It tracks the birth epoch and the retire epoch of each allocated node. The birth epoch is determined upon allocation according to the current global epoch. The retire epoch is set upon retirement and after the node is unlinked from the data structure. We use a type-preserving allocator. Upon an allocation of a node, a thread pulls a node from a designated allocation pool and makes sure that the retire epoch of this given node is smaller than the current global epoch. In this example, the retire epoch isn't smaller than the current global epoch, and they are both, since they are both equal to 8. In such cases, when the retire epoch isn't strictly smaller than the current global epoch, the thread must increment the global epoch before reallocating. Next, the thread reallocates the node by updating its birth epoch with the current global epoch and initializing its retire epoch. In general, suppose that a certain node is allocated and then retired. Later, another node is allocated from the same memory address. The global epoch must be incremented at least once between the retirement and the second allocation, which means that the life cycles of different nodes allocated from the same memory address never overlap. This brings us to the following observation, crucial for our optimistic reading mechanism. Stale values can only be read upon epoch changes, which guarantees that as long as the global epoch hasn't changed, all content read from shared memory is valid. Relying on this observation, VBR allows optimistic reads in the following manner. Each executing thread keeps track of the global epoch. Before accessing shared memory, it makes a local copy of the current global epoch. Throughout the execution, after each read from shared memory, it reads the global epoch again for making sure that it hasn't changed. If it indeed hasn't changed, then it may continue its execution. Otherwise, the program moves control to an appropriate location. This may involve restarting a traversal, exiting a loop, or similar solutions. Note that a read of a stale value necessarily implies a change of the global epoch, but not vice versa. However, we conservatively follow the validation failure protocol anyway. Correctness follows immediately from our previous observation. Stale values can only be read upon epoch changes, which means that as long as the epoch validation test exceeds, we never read invalid data from shared memory. If the validation test fails, All of the content read from shared memory is discarded, including stale values. Let me now focus on the need to handle validation failures. Memory managers sometimes cause a read or a write instruction to fail due to a memory reclamation validation test. This failure is not part of the original program control flow, and therefore must be treated carefully. In many known lock-free data structures, handling validation failures is easy, which makes the use of VBR and other reclamation schemes easy in practice. However, designing a general method to handle failed validations for all data structures can be really challenging. While most related papers do not suggest a general solution for this problem, we treat it formally and suggest a generic validation failure protocol. Its detailed description, along with the full correctness proof, appear in the full version of our paper. Before moving on to our optimistic writes scheme, I'm going to demonstrate our optimistic read mechanism together with a validation failure example. Consider this linked list. It contains 3 nodes with birth epochs of 2, 8, and 6. The current global epoch is 10, and all 3 nodes do not have a retire epoch as they have not been removed from the list yet. If the middle node here is deleted, then its retire epoch is 10, which is the current global epoch. It can be reallocated only once the global epoch turns 11. Moving back to the previous state, in which the middle node is not yet deleted, suppose that a thread T is currently traversing the list. It must first record the current global epoch, which is 10. After getting to the first node, the global epoch is still 10, and the traversal continues. After getting to the middle node, if the global epoch is still 10, it is guaranteed that the current node is not reallocated yet. This read is safe even if this node is deleted and retired while T still holds a reference to it. The remaining case is when the middle node is deleted, retired, and reallocated while T still holds a reference to it. In this case, T must observe the global epoch change. The validation failure protocol in this case is to restart the traversal from the list head. As I have already shown, this mechanism allows T to traverse the list while making sure that stale values are ignored. Moving on to our optimistic write mechanism, although associating each node with birth and retire epochs ensures read correctness, it does not prevent writes to reclaim space. In order to ensure that write accesses to reclaimed space are guarded from affecting program semantics, each mutable field is associated with a field version. The field's data and its associated version are always updated together. You can see here that the node's birth epoch is 7, its retire epoch is 15, and the version of its next pointer is 12. In general, all field versions are bigger or equal to the node's birth epoch and smaller or equal to its retire epoch. In particular, a pointer's version is always the maximum birth epoch of the respective node and its successor. Here, the pointer's version is 14, since it's the maximum between 7 and 14. And in another case, it is 7, since it's the maximum between 7 and 5. Note that our linked list example does not include non-pointer mutable fields. In general, Other types of mutable fields are traditionally associated with the node's birth epoch, and therefore are immutable throughout the life cycle of the node. As opposed to other mutable fields, pointer versions are not immutable throughout a node's life cycle. Therefore, they must be invalidated before retirement for making sure that they never surpass the node's retire epoch. Since the field's actual content and its associated version are always updated together, in most cases, this invalidation is already included in the given data structure implementation. For example, list pointers are marked as deleted before physically removing a node for preventing any future update. I'm now going to explain, using an example, why allowing optimistic writes also maintains correctness. As I have already mentioned, when updating a pointer from a certain node to another one, the pointer's version is set to the maximum birth epoch of the two nodes. Now, consider these two nodes. The pointer's version is 12, as it is the maximum between 12 and 6. If one of these nodes, say the middle one, is deleted, then its retire epoch must be at least 14, which is the current global epoch. In case it is reallocated, the global epoch must be incremented at least once, and its new birth epoch must be at least 15. If the left node points to the new allocated one again, the associated version will be at least 15. If a thread assumes the old value, it will not be able to update this pointer since its associated version has changed. In summary, while fully allowing optimistic shared memory access, VBR maintains the original program's correctness. Reads are safe thanks to the constant epoch validations together with the validation failure protocol. And writes are safe thanks to the field versions. VBR is obviously robust. If a node's retire epoch is equal to the current global epoch, then its reallocation includes a single atomic update of the global epoch. Otherwise, it involves no action at all. Therefore, the theoretical bound on the number of retired nodes that cannot be reallocated is 0, which derives robustness. However, frequent epoch changes reduce performance due to frequent cache misses and the inherent expensive retry protocols. We postpone the reallocation of retired nodes using local retire lists. The bound remains small with respect to the retire list size. Needless to say, VBR is also correct when keeping the theoretical bound in practice without using retire lists. For evaluating throughput of VBR, we implemented Michael's log-free linked list, a hash table based on this implementation, and Hurley and Shavit's log-free skip list. We evaluated VBR against an execution in which memory is never reclaimed. We also evaluated VBR against optimized variants of the original epoch-based and hazard pointers algorithms and against two hybrids, interval-based reclamation and hazard errors. Each test was a fixed time micro benchmark in which threads randomly call the insert, delete, and search operations according to 3 workload profiles. Threads call the search operation with a probability of 90% in the read-intensive workload, with a probability of 50% in the balanced workload, and never call the search operation in the write-intensive workload. Each experiment lasted 1 second, and was run with a varying number of executing threads. Each experiment was executed 10 times, and the average throughput across all executions was calculated. Here you can see the results of our write-intensive experiment, run on a hash table with a range of 1 million keys. We measured throughput in million operations per second as a function of the number of executing threads. VBR outperforms epoch-based competitors due to its infrequent epoch updates. Most global epoch accesses during VBR hit the cache and are negligible in terms of performance. In addition, VBR outperforms its pointer-based competitors since it does not require memory fences when reading. As shown here, VBR's throughput is around 65% of the no reclamation execution for the write-intensive workload. It outperforms the next best algorithm, EBR, by up to 40%. VBR outperformed its competitors in other data structures and workloads as well. As you can see here, VBR is faster than its competitors for a skip list and under a read-intensive workload as well. Other results appear in the full version of our paper. In summary, we propose VBR, a lock-free, bounded, and fully optimistic safe memory reclamation algorithm. We have demonstrated VBR's high applicability and efficiency against state-of-the-art competitors. Thank you for listening.